I think our application might be a little more extreme, where we're thinking of like a car flying 70 to 100 feet, landing and trying to stop a wheel at the same time. We're trying to make massive power, and we get this instantaneous deceleration plus torque from the engine. There's no slip in the drive line. The clutch is locked. Sort of something's going to give at that point. Hopefully it's the tires.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Dan from Vermont Sports Cars, or VSC for short. VSC are partnered with Subaru America and are responsible for developing Subaru's rallycross, and gymkhana program. Specifically, one of the standout cars that they are known for is Travis Pastrana's gymkhana car, which also broke the Mount Washington hill climb record, just making sure that it is not a one-trick pony. This thing produces around about 860 horsepower. This is a really wide-ranging chat with Dan. We dive deep into the development of a Subaru engine for rallycross, and gymkhana. We talk about some of the solutions that VSC are putting in place to ensure reliability. Particularly, there's a great discussion here around head gasket integrity with a rallycross engine, while ultimately they only produce 600 horsepower, which doesn't sound like a lot because of the way that power is produced with a 45mm inlet restrictor. These are running as much as 4 bar of boost at lower RPM, so the actual cylinder pressures are extreme, and that requires some really specific work in terms of head gasket integrity. Also, discussions around billet blocks versus cast blocks, factory blocks, and pros and cons. Also, a really good deep dive into the world of anti-lag strategies. We talk about traditional versus fresh air anti-lag strategies, pros and cons of those two techniques, as well as some great tips around how to ensure your anti-lag strategy is tuned reliably and isn't going to melt down your turbocharger. Now, before we jump into our interview, just a quick introduction for those who maybe aren't aware of what High Performance Academy is. We're an online training school. We specialize in teaching people how to build reliable quality performance engines, how to tune them, how to build reliable wiring harnesses, and we also cover other topics such as motorsport fabrication, driver training, and race car setup and data analysis. And we do all of this with a range of online video-based training courses that you can take from anywhere in the world. This allows you to learn from the comfort of your own place, and you can learn at your own pace. Once you've purchased any course from us, it is yours for life. You can watch it as many times as you like, whenever you like. And we also offer a 60-day, no questions asked money back guarantee on the purchase of any of our courses, so you can feel free to give them a test drive with absolutely no risk. Relevant to today's topic, we do have a range of courses on performance engine building, and we do talk a lot with Dan about engine building specifically. If you are interested in learning more, we have our Engine Building Fundamentals course, which will teach you, understandably, the fundamentals of engine building. What goes into building a performance engine? You'll learn about clearances, tolerances, the machining operations that go into getting your engine ready to assemble. You'll learn how to speak the same language as an engine machinist. That follows on with our practical engine building course, which will give you a really nice, simple 10-step process that you can apply to building any performance engine. You can then watch that 10-step process being applied from start to finish in our worked examples, where we go through a real engine building job from the very beginning through to a turnkey ready-to-run engine. As a HPA podcast listener, you can also use the coupon code podcast75. That's going to get you $75 off the purchase of your very first HPA course. And we'll put a link in the description to those courses that I've just mentioned. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Dan. Thanks for joining us today. And as we usually do, let's just get started with a little bit of background on yourself. Basically, I'm interested in knowing how you sort of got started working on cars and how you built up the skills that you've currently got.
Yeah, when I was a kid, my dad said I was always taking things apart, but not necessarily putting them back together, that classic thing. He always had the thing that I could use his tools as long as I put them back, so I was taking advantage of that. Then later as a teenager, when you get a chance to drive, I really fell in love with Volkswagens. So I had a lot of Golfs, GTIs, Rabbits, and growing up in Vermont, there's tons of dirt roads and intersections and fun places to go. So be lots of late night playing around with the cars. It was really more of a hobby. I never really thought it could turn into a career. I had taken a class at Tim O'Neill Rally School and really enjoyed it. So I reached out to them and I said, if you were going to do something in this field, what would you suggest? And they said mechanical engineering, which really at the time I was aware of, but I didn't know what that meant. So I started to look into it and I thought, this is something I want to try. So I decided to go to a tech school in order to learn the basics. And I enrolled in an associate's degree for automotive tech and also a 2-year degree for mechanical engineering. Those two combined.
Okay, so that's an interesting angle. I mean, for professional motorsport, often the mechanical engineering aspect becomes almost a non-negotiable, and particularly if you're going to get into component design and development, that engineering background is pretty important to understand the stresses involved, the loads that are going to be applied to a part, and therefore being able to understand what the part needs to be designed, how it needs to be designed in order to withstand that. There's quite a disconnect between that element and general mechanical engineering in terms of working on the car. So was the mechanical engineering side of it essential for what you're doing today, or has that just ended up broadening your skill base?
It is definitely essential for what I'm doing today. At the time, I really didn't know where I was headed. I felt like I wanted to do more than dealership work, although lots of people do very well there. I just thought maybe it would be hot rods or something more unique to work on. But once I started doing the mechanical engineering courses, I was like, this is definitely the direction that I want to go. And I ended up extending the degree at the college to electrical mechanical engineering. So I ended up doing a 4-year degree of electromechanical, and that combines mechanical engineering, computer science, and electrical. So you do a heavy focus in each one. And then the last year is sort of a capstone to bring it all together. In my 3rd year, I needed to do an internship. And that was part of the automotive degree. Most of the students would go to a dealership over the summer, and we had to work 400 hours as part of the degree. I was aware of Vermont Sports Car, and I was interested to do something like that. So I actually called every day for a month trying to get in. Finally
Persistence
got it.
pays off.
It did, yeah. I really didn't know what I was doing, honestly, but it worked. And I got an interview with Lance, the owner, the president of the company. And at the time, they needed someone to work with his brother, Colin. Colin was basically doing engines, transmissions, electrics, all on his own. And he was really busy. So I did my summer internship with Colin, continued to work there on and off on my breaks over my last year of school. And then when I finished school, they offered me a full-time job.
Right, so you literally straight out of school, straight into Vermont sports cars, and the rest is history. And now, to get us up to date, I've already discussed briefly what VSC is in the intro, but to bring us up to speed, could you give us maybe sort of the 30,000-foot view of what Vermont Sports Cars is, what they do, and then what your position in the company actually involves?
Sure. So 90% of what we do is for Subaru of America. So we run the rally and rallycross team for Subaru of America. And we also build special cars for them. media ride cars, different stunts, the recent gymkhana cars. Almost all of our effort is around promoting the Subaru brand through racing.
What sort of size are we talking in terms of the company? What size is your facility? How many staff in total have you got?
We just built a new facility in 2018. It's beautiful. If you go on the website, you can take a virtual tour where they kind of came through with cameras and you can see everything. I think it's 70,000 square feet, and we have 70 full-time employees.
Okay, so this is a serious operation, and I would urge people, once they've listened to this podcast, go check out VSC's website. That workshop is a work of art. I mean, it's as close as I've seen to F1 spec workshops, and it looks like you could pretty much eat your lunch off the floor in any particular place, and you're not going to catch anything nasty. It is immaculate. So congratulations on keeping it like that. I assume it still looks like that today.
Thank you. Yeah, you're right. We do have a little wear and tear, but it's always kept up, and that is a big part of what we're shooting for. We also do tours. So the building our old building was very difficult to get people in. And this one is constructed to be able to show people what we do. So on Friday afternoons, you can walk through and see what's going on.
Okay, great. Now, your position in the company, can you tell us what your title is and again, sort of what that encompasses, what you're involved with on your day-to-day?
Yeah, I'm the powertrain department manager. So I'm overseeing the engine and gearbox assembly. We have 5 employees there, and some of the technicians are mainly working on the engine, but most of them cross over. So we're supporting all the efforts for the cars that we're running. Last year we had 4 rallycross cars, 3 rally cars, the gymkhana car, a media ride car, and we're building some new cars. All of those, of course, have the engines in and gearboxes, but then we have spares behind them and a build rotation that we're working on, plus ongoing development. We're supporting the cars on the track, so we'll follow the build through the shop, run it on the dyno, check the calibration, run it on our chassis dyno, then go to the track and do the trackside support as well.
I'm interested to know, obviously, there's going to be a range here depending on whether you're talking a stage rally versus rallycross versus gymkhana, because they're all at very different power levels. But what's the sort of maintenance schedule on some of these engines in terms of how many racing miles are you getting on the engine before it requires a tear down, basic maintenance, full overhaul, etc.?
Now it's been really good. It was a long road to get there, honestly. So in the early days, it wasn't a question of when, if we would change the engine. It was when are we changing the engine. Now we have a lot of reliability, and last year we ran 2 rallycross engines for the full season in Nitro Rallycross. And in rally, we run usually about nine events, depending on the driver's schedule. We typically do them every 4 rounds. We'll do a rebuild, which is about 600 stage miles, 1,000 K.
I assume that's more preventative maintenance, though, because a failure in a rally is obviously a major blow to your points, as opposed to actually strictly being essential.
Yes, 100%. It's a lot cheaper to do, the basics of some bearings and seals and maybe a valve or 2 and the labor to rework it than to have something go further and have some serious damage. We do put the engines back on the dyno when they come out to see where the performance is. And usually they're making similar power, sometimes even a little better power than when they left.
All right, we'll dive into the tuning, the dyno element as we go through this, but just to sort of take a step back, what I'm hearing here is essentially VSC is a one-stop shop. So safe to assume you are literally doing every single element of the build in-house, fabrication, general mechanical. Obviously, we've talked about the engines, the dyno tuning, and you're also covering your own wiring requirements?
Yes, we have wiring. We have an electrical lab. We have a paint booth. We have a composites department as well. So there's 5 guys in the composites department, and they're building the bodies, all the bumpers, quarters, doors, wings, skid plates, parts inside the car like footrests and brackets and stuff like that. So they're tremendously busy with the damage that the cars see to keep everything going.
Yeah, unfortunately, bumping into things does seem to be a natural sort of requirement with rally as opposed to circuit or road racing. Seems to, normally, but not always, keep the cars a little bit straighter. So I'm sure that composites department is kept pretty busy. And that having everything under the one roof, does that just help with streamlining everything because you've got complete control over every element that goes into a build or an overhaul of a car?
Yes, definitely. I should also mention we have a design office. So we have our 4 to 5 design stations, and we have an inspection room that we have a ferro arm so we can scan the cars or pick up points. But having all of this under one roof gives us tremendous control and flexibility. Sometimes it's a challenge to rein in what could be done, and we can be too reactive in a way.
I guess everyone's got a budget, even corporates like Subaru America.
We definitely do. It's almost like an opposite of most businesses. We start with a check and we dwindle it down, but we still have to have a budget and control that. But sometimes, we've pulled off some miracles that we've had a major issue that needs to be fixed, and we can do it all in-house, and it gets done, and the car leaves the next day. So that's happened a few times.
Yeah, that flexibility must be really important when you do have a problem to work through. Now, I'm interested to know, obviously, it's been a long-formed relationship, but how did it come to be that VSC formed this relationship with the Subaru platform?
Around 2001, ProDrive was rallying in the U.S. with the WRX. Subaru had brought the WRX to the U.S. at that point, and VSC had supported that effort. So there was a connection then. And then in 2005, Subaru America selected VSC to do the rally program. We were just focused on rally at that time.
Okay.
Really passionate about rally, and of course so is VSC and the owner Lance. So that was a good direction, and also Subaru was a great car.
Interested to know that relationship with ProDrive. Is there still a relationship there? I mean, ProDrive obviously build Subaru's WRC cars. There's a technical knowledge and understanding that they obviously have at that level. Is there any sharing of information, or have you sort of split and gone your own path now?
In the early days, we did purchase components from them that, like a restrictor or a special silicon hose that they made. There is some crossover that quite a few of the technicians or engineers that are more like the mercenary technicians that would fly in have experience from the WRC days working with ProDrive, but we haven't been working on projects together.
Okay. All right. The actual Subaru platform, and I don't want to maybe annoy the Subaru fanatics out there who will be listening to this. I definitely don't have anything against the platform, but the reality is that we see, even in lightly modified road applications, people do struggle with reliability, particularly around some of the aspects of the engine. So I would say sort of objectively, it's a platform that will present some issues you're going to need to work through to make a reliable rallycross or gymkhana car. And hopefully you might agree with me there. The question really is, what are the main weak points or weaknesses that you need to address with that Subaru platform, and what are you doing there?
I think the main thing that we focus on from the beginning is the oiling, the lubrication. What we found is the cylinder heads can be a large leak. So we definitely restrict the oil to the heads. And the purpose is to make sure that we have oil going to the main bearings. There's a significant improvement in the main bearing life if we restrict the oil to the heads.
So essentially what you're saying is, in stock form, there's too much oil flowing into the cylinder heads, and that's reducing the volume and hence pressure that's actually reaching the critical components, which are the bearings.
Yes, definitely.
Another element there is a lot of production engines run a hydraulic lifter because it's maintenance free and doesn't require the lash to be adjusted. That does require additional oil flow, but if you convert to solid, or you're starting with a solid lifter arrangement, then the oil flow to the heads would be hence reduced anyway.
I mean, there's a massive amount of oil in there. It wasn't an experiment done on purpose, but if you don't put the gasket in around the spark plug access hole, oil will pour out. Just to give you an idea of like how much oil can be in there. So we have been able to restrict oil to the heads, block off the exhaust buckets completely, because we have oil coming down from the inlet buckets.
So it's like a natural sort of drip lubrication to those components.
Correct. And the cam as well. We have also changed the buckets to DLC, but we've run them without the DLC, with the galleries blocked off, and that's been fine.
That DLC coating, let's just talk about that for a moment. It's not actually something that I've had experience with, but I broadly understand what it is. Diamond-like carbon, I think, is the what it's short for. And this is a coating that helps reduce wear and friction. Is that correct? Yes, it's an extremely hard coating. We can coat the camshafts and the buckets, and it reduces the wear and the friction. So when you have the sliding surface, there's a tremendous amount of stress, and that reduces the friction in that area. It increases the life as well. So in the worst case, if there was some damage and the DLC cracked, it could start to fail, but otherwise it holds up for a very long time. We also, right away, we would put in case bolts. It's really important to keep the main line together. So if we have distortion of the main line, then the oil is going to leak past the main bearings and not feed the rod. So the ultimate failure is spinning a rod bearing, and the root cause usually is that the main line is distorted. When you say main line, you're talking main bearing tunnel there. Yep. And in the Subaru, that's down the middle with the two halves coming together. It's quite a unique sort of engine design with the boxer horizontally opposed engine, which again introduces its own idiosyncrasies. But one of the things that I think is really easy to overlook with people building sort of mildly modified street Subaru engines is in terms of, the likes of ARP, just one that springs to mind, do a set of case bolts or studs for the engine. No problem, stronger material than stock, additional clamping force, all sounds great. The problem with it is when you're dealing with an alloy block, that alloy is relatively soft, it's not a cast iron, and it will distort. So the number one sort of failing point I see is people don't realize that when they upgrade to a set of ARP studs or case bolts, that it actually is essential to have that main tunnel line honed to get the tunnel back to truly round and make sure that the bearing clearances are correct. I assume that's something you're dealing with in-house as well? You're right that when we torque the main case bolts, we go to higher torque than the factory torque, and that will distort the main line. So we're actually working with an engine machinist that has a special machine to do all the work we need in one setup. So we don't have to separate the block halves, and that can cause perhaps some issues getting everything back together in line. So we have everything clamped to do the main line and the liners in one setup. He's able to rotate the block on a fourth axis to do that. Okay. But we definitely need to be in line or speaking the same language with the engine machinist of what the torque will be in the torque sequence, so that when it's finished, it will be at the correct size. That's definitely critical. There is reliability, I would say, in using the case bolts, and it's mandatory on everything that we're doing. I think a good case for the case bolts, pun not intended there, is anyone who's ever pulled apart a Subaru engine or split the two halves of the case on one, particularly one that's making a reasonable amount of power, and almost inevitably you're going to see signs of threading between those two halves of the case. And that simply straight away makes you aware that those two halves of the case have been separating even marginally, just thousandths of an inch, and physically moving relative to each other. So that gives you an indication of what's happening. And we obviously can't have that. We don't want that, because when that splits, that introduces, among other problems, an oil leak. So you're essentially losing oil pressure. So I just wanted to talk about that, why that's important. The other element I'll just bring up here, and I'm pretty confident I'm going to already know your answer. The only reason I raise this is because it's come up a couple of times recently, and I've got my own very strong opinions on this. The problem we've just talked about, where you use an aftermarket stud, talk to the manufacturer's recommendations, and that's going to distort the case. So a lot of people, and I see this in both the Subaru and the Honda platforms, will go to an ARP main stud and then simply under-torque the fastener to avoid distortion. Interested on your take on that technique, because it surprisingly seems pretty well spread across the industry as an acceptable technique.
Honestly, I haven't heard that. I guess we're just operating in our own world, doing our own experiments, but we've gone the other way, and I would say we're 50% higher than recommended. Which definitely distorts everything, but then we're straightening back out. But the spring that you get when the bolt is torqued correctly is allowing for some distortion, and the bolt will still keep everything clamped together. If you imagine that you need to have a stiff joint that the bolt is going into, but then the bolt is stretching maybe microscopically, and that's providing like a spring, and it's providing the clamping force. So if you're loosening that, I would feel you're going to have a much smaller margin for having distortion and being able to control any movement that's going on. Also on the movement you were talking about, we run what's referred to as anti-shuffle pins. So we pin the two halves together. I think quite a few people are doing that now. But essentially using machinist fixture pins that you can get all over the place. And then on the number one, where the bolts go through, we use ring dowels, so we can still pin it together and have the bolt come through.
Yeah, glad that you actually brought that up, because that was another question I had. I think that's something I've seen with quite a few high-end Subaru builds, and in stock form, essentially the two halves of the block, which make up one of the main bearings, aren't positively located. So you're adding that in the aftermarket to help again prevent that relative movement and that fretting. Before we move on with the stud situation, while you obviously haven't heard of it, it's been brought to my attention a few times recently, both on our forums and in some other sort of conversations I've had with those in the industry. And my point would be just don't. If you're going to go to the trouble of installing an aftermarket stud, do it properly. At least use the manufacturer's recommendation. Understand that the distortion will occur, and it's something that we deal with because our machinist line hones it. Otherwise, if you're not going to go to that trouble, you're just wasting your time, in my opinion. So, just wanted to clear that up. Another issue, while we're talking about the bearing issues, and you've mentioned spun big end bearings, which can come as a result of this lack of lubrication because of all the other things we've talked about already. One of the problems with the Subaru crankshaft, given that it's very short, if anyone's actually seen a Subaru crankshaft out of the engine, it is a very short crankshaft, and by virtue of that, it means that our big end bearings are really, really narrow compared to the likes of most conventional inline four-cylinder engines. Does that in itself pose additional problems for load handling capability of the bearing, or if we get the oil control correct, does that issue just go away?
We have redesigned the lubrication in the crank, so how the oil is fed the bearing, and I think that's helped us the most. Once we've done that, we're also using custom motorsport bearings, so they're very high end, very expensive. What we see now is just a fracture of the overlay. If there's some trauma, like an abnormal situation, apart from that, they come out looking almost like new. You can still see the measurement marks that the guys use to set it up. I think it depends on the usage, and we've had really good luck with a lot of the aftermarket bearings as well, but we just have a very extreme usage case, so we had to go for the very high-end bearings.
Sure.
But I know what you mean. We were concerned about, if you look down, like the projected area of the bearing is a lot more narrow. But I think if you have good oiling there and you're not making contact, then we haven't had any issues.
I think that's the part that's easy to overlook for those who aren't well versed in engine building. There's this assumption that the bearing surface runs on the crankshaft journal, and of course, nothing could be further from the truth. If everything's working as it should, there is no metal-to-metal contact, and we're protected by this layer of oil, and that's critical because almost as soon as we get any metal-to-metal contact, if that crankshaft journal pushes through that oil film and actually contacts the bearing, we're almost guaranteed instantaneous failure. So I just wanted to get that out there. And I don't know your take on this. Maybe you're just not working in that level anymore. But I mean, I was in a situation where I was tuning a lot of stock, lightly modified through to moderately modified street-driven Subaru engines. And I think one of the reasons that I saw for big end bearing failure was actually tuning related. And that might not make an immediate sort of connection. The correlation there is not necessarily that obvious. But the problem I saw was, and this is actually interesting because I find straight off the showroom floor, at least the locally delivered Japanese domestic market Subaru STI and WRX, the ignition timing and the factory calibration is actually too aggressive for our local fuels. And with zero modifications, there's quite a significant amount of knock activity occurring. And it's that gets worse, obviously, if it's poorly tuned, more boost, maybe a linear fuel ratio and too much timing and knocks occurring. And it's that knock creates almost like you could think of someone smashing down on the top of the piston crown with a sledgehammer. And while most people think of knock-related failures in terms of melted pistons or damage to the piston, it's that constant hammering on the top of the piston being transferred down through the connecting rod and then into that big end bearing. And that, in my experience, I've seen a lot of bearing-related failures as a result. So get the tune right, and a lot of those problems that Subaru gets a bad name for in street applications, they just go away. Do you you've seen anything like that as well?
I follow what you're saying. I haven't seen that directly. I think our application might be a little more extreme, where we're thinking of like a car flying 70 to 100 feet, landing and trying to stop a wheel at the same time. We're trying to make massive power, and we get this instantaneous deceleration plus torque from the engine. There's no slip in the driveline. The clutch is locked. Sort of something's going to give at that point. Hopefully it's the tire slipping, but if not, that's when I think we might see this sudden shock load that gives us some distortion.
I'll admit that none of my customers were doing 70 to 100 foot jumps, so I can't speak to that. But yeah, I can only imagine there'd be some problems associated with your very extreme applications. Before we move on from the oiling system, is it safe to assume that you're going dry sump with these applications, or is it not essential for every use?
So just until last year, the rally cars were wet sump. We've recently updated them to dry sump, so now everything's on dry sump. But we were using wet sump successfully for quite a while.
Is that just in relation to the lateral and longitudinal G-force that you can generate in a rally application versus road race, or is it down to the development in the sumps in terms of baffling that you can get away with that?
The real underlying reason we went with the dry sump was we had introduced some technology we had left over from rallycross. So we were trying to update the rally cars with components we had from rallycross. On the rallycross, we tried to integrate the dry sump as much as we could into the heads, and it was difficult to go back to wet sump. So it was easier just to apply the dry sump into the car than to try to undo everything we did to make it a dry sump engine from scratch.
Sure. Okay, that makes sense. Now, could you maybe just give our listeners a brief kind of high-level overview of what the differences in the specifications are for stage rally versus rallycross versus gymkhana, just so we've got a bit of an understanding there and we can dive a bit deeper into the individual ones?
Yeah, the sports rally and rallycross almost feel like they're inverted, where the rally cars will go away from us. They're on closed public roads. They'll complete several stages, then come back for the service. Whereas in rallycross, we basically live with the cars all the time. They just go away for a couple minutes and come back hot and sometimes broken. And then we work on them for hours. So they're quite a bit different sports. In rally right now, we're mandated to run a 34 millimeter restrictor on the turbo, and there's also a boost limit. So with the restrictor, you can make about 330 to 350 horsepower, depending on the application. In rallycross, it's a 45 millimeter restrictor on the turbo, and then we're shooting for 600 horsepower. Gymkhana has no restriction. It's just for video. So we're applying some restrictions because we need to hopefully make it through 5 to 7 days of filming without a lot of trouble. So we want maximum power and performance, but then we're self-limiting boost or torque or the power curve to stay within the reliability that we know, to avoid any issues. Once the cameras are rolling and everyone's down at some location for one of these big films, it's also really high pressure. So we don't want it to be on us that everything needs to stop. So we need to find the right amount of performance, but also hopefully we're not really winning anything there if we, get that extra 10 horsepower out of it.
Yeah, I get you're not racing against the clock, and probably no one watching Gymkhana is going to know if Travis had 860 or 790 horsepower under his right foot. It makes no difference. I can only imagine with a full production TV crew, movie crew, and maybe a helicopter up in the air, if there's a downtime for a mechanical failure, that's going to get pretty expensive pretty quickly. Yeah. Let's just come back to the rally spec engine, and you mentioned this 34 millimeter restrictor versus 45 for rallycross. And for those who have no clue what you're talking about there, can you just tell us what that restrictor actually does and whereabouts it's located in the engine?
I guess you may have heard of restrictors like restrictor plate racing is a term. In our case, they're limiting the airflow that can go into the turbo. So we have essentially, it looks like a cone that goes in front of the turbo, and it's converging down to a diameter that's mandated by the organizers. So for rally, it's 34 millimeter.
And is this essentially a way of leveling the playing field for all the different manufacturers? So regardless what engine specification you're running, what manufacturer the engine's from, etc., that is ultimately the limiting factor on how much air you can get into that engine.
Definitely. They kind of look at it, the restrictor limiting the air and therefore the power it can produce. And then they'll also usually have a minimum weight of the car. So those are kind of basic rules that would apply. The restrictors also use the limit performance for safety. So they're always looking at what the top speed of the car is on the stage, and they're trying to balance the risk that maybe the drivers are taking. And they can ask us to run smaller restrictors. So over the years, we've run larger and smaller restrictors depending on what they're seeing.
Okay. In terms of the restrictor, and we'll talk a little bit more about this as well, it does affect the turbo performance, and it affects the boost pressure that we can run, particularly in terms of the boost curve relative to engine RPM. And you've mentioned there, this is something that I don't believe we have in New Zealand with rally. You mentioned a boost limit on top of the restrictor size. So what is that boost limit, and how does that sort of play out?
Right now, the boost limit is 2.8 bar, which would be absolute, or 27 PSI. So we monitor the restrictor to get the most amount of performance we can out of it. So in the middle of the restrictor is the actual diameter that we must run. And there's a cone down to the restrictor, and then it expands back up to the turbo. If we're maximizing the restrictor performance, then we can't get any more mass through the restrictor. And that term is choked flow or sonic flow. So when the restrictor is choked, there's no more mass that can come through. We've got all the air that we can get through. We don't want to go beyond that, and we don't want to be less than that because we would lose some performance. So we have a sensor that we put on the front side of the restrictor. We can't have it on the back side because then you might be injecting something into the turbo or allowing more air to pass than is allowed. But we have a sensor on the front, and as the turbo speed increases, then the speed of the air going into the restrictor increases. Then the pressure drops. So we're watching the pressure drop as speed increases, the turbo speed increases. And as the turbo speed increases, boost increases. And we'll get to a point where the pressure is dropping and dropping in this pre-restrictor sensor. And when we hit the choke flow, it will flatline. If you go beyond that, it won't drop anymore. So that tells us we've reached choke flow, and that would be our goal. So if we have the ability to run more boost before we hit the choke flow, then we're on the boost limit. And then we'll be adding more turbo speed until the point we hit choke flow. And then we're trying to maintain that bull curve.
Okay, so a bunch of stuff to sort of go back and unpack. Really interesting to get some insight into how you're using that sensor. So first of all, just the non-choked flow versus choked flow. So generally, and I mean, I haven't seen what you're doing, but I'm going to assume here what that means is that at low RPM, maybe sort of 4,500 RPM, you're not restricted by the restrictor. And it's that boost limit. So you'll be sort of right on that boost limit. And then as the RPM increases though, and generally these restricted engines, we don't tend to rev them too high, the boost will tend to fall away. So you've got a very pronounced boost curve. And I think a mistake probably everyone new to tuning restricted rally engines has made is trying to treat it like an unrestricted engine and run a flat boost curve. And you A, can't do that, but B, what you find, which is a bit counterintuitive because of this choke situation, is that at higher RPM, you may be able to run more boost and you'll actually see less power as a result, and basically you're just superheating the air. So by actually reducing the boost and getting back into that sort of right on the edge of that choke flow that you've mentioned, that's where you're going to optimize performance. So just a little bit counterintuitive for those who haven't actually dealt with restrictor tuning before. Now, I'm guessing if you could have a sensor post-restrictor, pre-compressor, that would actually be the sensor you'd really want. You've mentioned you're not legally allowed it, and then you'd be able to actually actively monitor pressure ratio across the compressor as well. That would be a valuable input if you're allowed it.
Yes. So in testing on the dyno or in the car, then we'll have that extra sensor after the restrictor. If we come down to choke flow, I guess both pressure sensors are dropping at the same time as we increase turbo speed. When you come down to the point where you've reached choke flow, then the pre-restrictor pressure stops. But if you keep increasing turbo speed, then the post-restrictor pressure continues to drop.
So you're essentially pulling a vacuum post-restrictor pre-compressor.
Correct. Yep. And then, as you mentioned, the pressure ratio, ideally we would get back to atmospheric pressure. But they also limit by regulation the distance between the compressor wheel and where the restriction needs to be placed, which is about 50 millimeters. So that gives you some distance to expand back up, but not enough to get all the way back to atmospheric. But the main thing we don't want to do is also be over choked, because then we'll be pulling it down too much and you will lose performance there too. With the restricted engines, and there's a maximum amount of performance we can make, then a couple percent means a lot. And even 1% means a lot in the power. And making a mistake of being over choked, you can lose power. So, we want to avoid that. Ideally, you would see the pressure curve come down and it would just ripple on a straight line. And then you're right at choke flow. And sometimes you need to test that, push it a little harder to confirm or come off a little to confirm. But that's maximizing the performance.
Okay. You've already alluded to the fact there that this is very competitive and just a percent or two is going to make a big difference in the hands of a competent driver. This is also now a very well-developed platform, both with the engine technology and these restrictors are a known entity. They haven't changed. What are you doing in terms of engine development? Is there still more available? I mean, obviously, ultimately, you have this maximum mass of air that you've got to work with, and that's what the restrictor is limiting. So what are you doing in terms of being more efficient with the use of that maximum amount of air and extracting as much power from it as you possibly can? And what sort of development's being done there?
We did a tremendous amount from 2017 to present. We made our own cylinder heads. So we made billet heads and then made a cast version of the same head. They're basically interchangeable. So we worked a lot on the cylinder ports for that. We also did a lot of work on the intake manifold and camshafts. And that was an exciting and very interesting period of time where we were working on cams, compression, intake. And it was this big iterative loop where we would advance things and then have to go back again, advance meaning making more power, and then have to go back and revisit what we left before. We learned a tremendous amount, and now that's what we've been running for the past 2 years in rallycross, and now is trickling into rally as well.
Okay, I'm interested to dive in a bit, and I'm not sure if you can share some of the specifics here. I mean, they're not going to be too relevant to our listeners realistically, other than from an interest perspective. But in terms of compression ratio, obviously there's sort of a relationship here between the octane of the fuel we're running, the boost pressure that we're running, and the compression ratio. So we can't sort of consider one without the other two. We already talked about peak boost there. What is the control fuel that you're running, just so we've got a sense of that? We've
had different fuels through the years, but it's been E1, which was the World RX fuel, which is a 102 octane. We've had BP R5 and BP R5.1 as the fuel today. So they're all very good race fuels.
Still a petroleum-based fuel as opposed to ethanol-based?
This year they're allowing an ethanol-based fuel in rallycross, which is what we're expecting. We're still waiting on the final regulations, but they're leaning towards a biofuel to have a green fuel, which would be E80.
Okay. All right. So we've got a good quality fuel, which obviously is essential in making power reliably. So yeah, in terms of the compression ratio, can you give us a sense of where you ended up, or is that sort of proprietary?
I don't think we want to give the exact number, but it's higher than you would imagine, I would say. But I think where we gain the most is running a version of the Miller cycle. So if you think of the valve events, if we delay the intake valve closing, then we've changed the relationship between the compression and the expansion.
So you've actually reduced the compression versus the larger expansion ratio for a given compression ratio.
Yes,
that's quite often done with variable valve timing, so you can run in millicycle. Are you running variable, or is that's fixed? It's
fixed. Yeah, okay. It's not allowed. Yeah.
So the advantage, as I understand it, with millicycle is it improves the efficiency of the how much we can extract out of the fuel and air that we're burning. Is that correct?
Yes, definitely. I think it's usually more aimed towards lean burn for fuel efficiency, but combining the compression ratio with the cam timing allowed us to try some things that we probably wouldn't have thought would work initially. We were able to gain a lot more with the expansion ratio, and running a later valve closing that really brought quite a bit of performance for us.
Okay, this is quite interesting, and it's probably sort of might be a little bit beyond some of the people listening. So maybe go and Google millicycle and then come back to this, so you've got a better understanding of what we're talking about here. Now, my understanding of it is, while the millicycle, the increased expansion ratio for a given compression ratio is going to allow us to extract more efficiency or power for the fuel air charge being burned. The downside is essentially because we're reducing that compression ratio, we're reducing the volumetric efficiency of the engine. We're getting less fuel and air in during the intake stroke, so we can benefit from that increased expansion ratio. So, I mean, obviously, what you're saying here is that the benefits outweigh that reduction in VE, correct?
Correct. Yep.
Okay. Yep. Interesting. Not something I've had the opportunity to talk to someone about before. So, that's great to get some info on that. All right, so in terms of the differences between the rally engine and the rallycross engine, we know you've got that 45mm restrictor, so that's going to basically give a lot more air mass, make a lot more air mass available to the engine. You've said that there's 600 horsepower, which, I mean, most people listening would probably think, well, that's not really a huge amount of power, but I think what's easy to overlook is the way that power is delivered. So that restrictor allows very high boost pressures through the low RPM and mid-range. So the actual cylinder pressures are massive. And then as the RPM increases, while they're still going to make more power than the rally engine because of that bigger restrictor, you're again getting this quite sharp drop-off in boost pressure. Is that sort of a basic summary of the situation?
Yeah, you've got it. It is a 2-liter engine, so 600 horsepower of 2 liters is highly stressed. We have been able to work with some NASCAR teams on some different projects and compared notes, and we're 1.5 times the cylinder pressures that they would see. So they were kind of blown away with what we were up to. The boost curve does drop. So then through the RPM range. So the torque generally, if you're looking at the dyno graph, it's kind of falling away at like a 45-degree angle, but then the RPM is helping with the power production. So, we're always trying to get the most usable power range that we can, the biggest, broadest curve that we can. But realistically, we need to focus in on an area of 1,000 to 1,500 RPM to say this is where we expect the driver to be working most of the time, get the gear ratios right for that. But there can be many situations where it makes sense to stay in a gear and rev higher or lug lower and avoid that shift. So having the most broad range we can work definitely pays off in racing. So overall, we're working on the dyno from 3.5 to 7.5, regardless of the area that they're actually using. We just want to make sure if they go there, it's maximized.
Okay. In terms of the difference in the rev range between the rallycross with a 45mm restrictor and the rally engine with a 34mm restrictor, can you give us a sense of that? You've just said 3.5 to 7.5 for rallycross.
Yeah, the rally tends to be much lower. It's between 4 to 5.5, and the rallycross is in the higher RPM from like 5 to 7.5 that they're working.
And that's really with the 34mm restrictor, there's just no real benefit in revving the engine further. So the driver is typically short shifting, except obviously if you're in top gear and you're on a long straight, well, it is what it is. You're going to rev the engine as far as you require. Yep.
There's still a possibility to stay in a gear or lug it down, and sometimes they'll do that. But if you're going, from the launch, straight acceleration, then our shift lights are right at these RPMs to stay in the power curve.
Yeah, okay. Coming back to rallycross, so we've talked about the sort of boost levels for rally and the choked flow. Can you talk, I assume with the rallycross engine, you're still in exactly that same situation where you're trying to maximize the flow through the restrictor and run right on that limit of the choked flow. But what sort of peak boost pressures are we actually seeing down in the lower RPM where you're not so choked?
I mean, it can be quite high with the motorsport turbos. They can go up to 5.5 bar. Not that we necessarily go there, but they have that potential.
So talking absolute there.
Absolute, yeah.
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 Okay.
We could see 4 bar.
And this is really why we're seeing such massive cylinder pressures down in that lower RPM range, which sort of seems maybe out of context with the peak power level of only 600 horsepower. I say only 600, but as I mentioned, I mean, that's not an unheard of value now for a mildly modified street engine.
Sure, definitely. Yep.
Okay. With these cylinder pressures, we get problems that are twofold. First of all, the Subaru engine is essentially trying to split itself in half, and we've already talked about that aspect, so I won't dwell on that too much. This also comes into that element we're talking about with the reliability of the big end bearing, even staying away from detonation. The cylinder pressure physically just pushing down on that piston is just huge. But the issue I'm interested in is the aspect of cylinder head gasket integrity. And I mean, from my drag racing background, this was always kind of the limiting factor for me with my modest engineering capabilities and budget of how much power we could make out of this time a 4G63. But I can only assume that's an area that's required specific focus for the rallycross program. Are we allowed to get some understanding of what you're doing in terms of head sealing?
Yeah. So on the head, we're not using a head gasket. We're machining the block to receive a gas ring. So this is like a metal O-ring that's crushed when the head is clamped on. It's a technology that's been used in rally by other teams. We needed to make our own version of that in order to withstand the loads that we have. So the gas rings we were using initially were not coping, and we could have some failures. But we did some iterations with the company designing those, sending them back samples, and now we have really good results. We're not lifting heads. That's kind of a known issue with the engines as well when you're really pushing the high cylinder pressure. One thing that we found when we introduced the billet block, we kind of blamed a lot of stuff on the OEM block that probably wasn't fair, because once we got the billet block in, we still had the same problems. So it forced us to address some other issues. We spent a lot of time on cylinder head torquing, the process, and how to keep it consistent, and kind of went back to basics with that. We did a tensile test on the head stud, so we had information about the strength of the stud, and then drilled a block so we could measure the stud from both locations, and we had our technicians torque the head a bunch of times. It's kind of boring for them, just keep torquing it and then measuring from both sides.
When you say measuring from both sides, you're talking about measuring the stretch of the fastener, which is really what we're trying to achieve when we're using a torque or a torque angle method. Is we're trying to achieve a specific amount of stretch in the fastener, because while they look really strong and stiff, basically a bolt, a stud is just a very, very, very stiff spring, and we're trying to stretch that a certain amount so that we've got the correct clamp. So the problem, of course, when we can't measure both sides of it, like we've got that issue in a blind hole, is we're trying to essentially infer stretch via a torque or torque angle, which may or may not be particularly accurate. I'm guessing that's the direction you're going on with this convo?
Yes, definitely. And we also found that the effect of the thread pitch, so when you're using these very big studs, then usually you're going to a quite aggressive thread, like 14x2. So a very small difference in angle can actually advance the stud quite a bit. So you might not perceive that the stud is moving, but while you're torquing, you're not actually stretching the stud, you're rotating it. So we spent a lot of time on that, and that combined with improving the gas ring has now been very reliable for us. It's allowed us to push to these upper limits that I think before probably would have been achievable, or we'd be changing the engines more frequently to keep up with it.
Okay. An element that we haven't talked about so far is the bores themselves. And I can only assume in these higher horsepower applications, you're moving to a full sleeve as opposed to working with a factory liner?
Yeah, we have two options. We're either using a ductile iron or Nicosil. Depends on the application. In either case, it's a pressed-in liner, so it's similar to the factory installation. We are using steel liners, either for the ductile iron is a steel liner. The Nicosil is also a steel liner for the load that we're seeing. Some people would use aluminum, but we prefer steel based on the combustion pressure and the load that it sees.
So the steel's much stronger, but we can't run the rings directly against the steel, so that's why you've got the Nicosil coating on that steel sleeve?
Yes, and the Nicosil is friction reduction. It gives better sealing if you get the break-in done correctly, and it will hold up a very long time, kind of like the DLC we were talking about. As long as it doesn't start to break down or crack, it almost looks like new when you inspect it again later.
I guess that does bring about a little bit more complexity around freshen ups in terms of you can't just re-hone it and put it back together. It'll need to be recoated. Is that correct?
Be replaced actually.
Replaced, okay.
Yeah.
Yeah, okay. All right. Now, you just touched on before the billet block. So this really comes down to, let me check, it's the VT20G, which was the gymkhana car that was famously driven by Travis Pastrana. Now, billet blocks these days are becoming more and more common. Particularly, we do talk to a lot of people in the drag scene, and obviously when you're sort of getting four-cylinder engines up and around the 2,000 horsepower at the wheel mark, it's difficult but not impossible to do that on a stock engine. In your application for Travis's engine, I believe it was around the 860 horsepower supposedly. Is that, in your opinion, an essential element, or could you have done that on the OEM block?
I don't think we could have done it on the OEM block. I think if you were in the range of 400 to 500 horsepower, what you're talking about before about reliability issues, I think that the OEM block supports that very well. From what we've seen, pushing up over 500 and the amount of distortion we see in the main line, it would not have supported it. Also, I think our power curves, as I mentioned before, are very broad. So it could be different to make high power at a very high RPM, but we're trying to push the torque constantly. So we're making massive cylinder pressure in the low end, as you were mentioning, but continuing that up as high as we can. And it's just maximum stress on the engine. So definitely I think the billet block is necessary.
Okay. What specific design elements have they introduced with the billet Subaru block that allow this sort of increase in cylinder pressure and keeping reliability?
We've been working with Crest CNC in Australia, and he had an existing block that we've been working with. And then we worked with him to make our own program on top of that to make modifications. The first thing is the base material is 6061 T6. The OEM block is made for 300 horsepower and fuel economy. So there is some porosity in there, whereas we start with a known good base material that can withstand the loads. That's bringing a lot. Then the design also has much wider bulkheads. So the main bearing supports in the engine are slightly trapezoidal. So they'll widen as they go to the block half. And then throughout the block, there's more material around the head studs in different stress locations. He did try to go too aggressive with lightning at one point and found some cracks. So there is still a limit, the material and the billet design doesn't fix everything. But once we got that sorted, then that's provided us a very strong bottom end and allowed us to work in a lot of other areas once that was kind of taken care of.
With a project like the gymkhana car, obviously there's no real rule book that you're working with. You can do whatever you like to get the end result. So I'm interested, where did you end up with that particular engine in terms of capacity? You go a little bit larger in terms of being able to spool a larger turbocharger and still get a usable power band, or is this sort of a trade-off here with rod to stroke ratios, etc., in terms of making the engine usable as well?
Yeah, so there were a lot of different ideas in the beginning, but for how much power they wanted to make. In the end, it was to go over 800 was the request. We have a lot of components that we know that we've worked for a long time on, so we wanted to use those in terms of reliability. So we stayed with the 99.5 millimeter bore, and that gave us 2.3 displacement. So the change in displacement from a 2 liter to 2.3 doesn't sound like a lot, but it is like a direct percentage in the power capability of the engine. We also are working with Garrett Motorsports through the Subaru of America agreement, and we developed a turbo with Garrett that was one of the largest flowing turbos in that frame. So we're using a single turbo to make this power, and they'd only made one other, they said, that was in that range. We really wanted to make it with one turbo so we could exchange it with our rallycross turbos as well, depending on the need for the car. So the car's gone on to do drag racing and hill climbs and so on. So we have the ability to exchange turbos depending on the needs at that time.
So you can change turbo spec to change the power band depending on what the application is. And obviously if you're doing drag versus gymkhana versus Mount Washington hill climb, the needs are very different.
Yeah, it can be more about response than just full power.
Now, I did want to talk about these turbochargers as well, because I'm going to assume with your arrangements with Subaru America, you're not dealing with production off the shelf turbochargers the likes of us mere mortals get access to, and Garrett do have their competition line of turbochargers, the TR30R, I believe, which essentially is also as a term pretty much meaningless. Was the way I understand it, they really are specified in terms of compressor and turbine wheels, etc., for a particular application. Can you tell us how one of these turbochargers differs from a G25 660 that we may have access to in the aftermarket?
Yeah, so the frame size that we would typically use is either a 30 or a 35. In some applications, they might go down to a 25. So you'll hear 25, 30, 35. Then the TR, 30R or 35R would have ball bearing. So it's got a very robust bearing system. Working with Garrett, they have quite a range of options. So you could have an iron housing, a titanium center cartridge. They have a family of compressor wheels that you can choose. So we'll talk to them about our application. They'll provide us several compressor maps that we can look at. And then we'll plot out where we expect to be running, select compressor wheels depending on where we think the best match is. And then they have different turbine housings as you can get in the aftermarket. Probably one of the biggest differences is the temperature that it can run. So we can run 950C continuous. We can have moments over 1020C. We can have over temp and we can have over speed. But if you have both together, then that's the biggest issue, because the wheel is growing with temperature and it's trying to bend or expand with speed. And if you have those combined, then you finally can get contact. But as long as we're respecting the temperature and speed limits, we can push them much more aggressively with the anti-lag or full power EGTs. and they can withstand it. They are expensive, but they're fully rebuildable. So we'll send them in for service, and it can be worth the investment.
No doubt. I think from my understanding as well, one of the advantages with these turbochargers is because they are motorsport or competition solely, and the public can't get access to them. They don't need to meet Garrett's consumer burst containment regulations, which in short means that the compressor and turbine housings can be much, much thinner, and what that adds up to is a massive weight saving over a conventional aftermarket turbocharger. So just interesting to know. A lot of people probably aren't aware that that's even a line of turbochargers, and these are used in WRC and Le Mans prototype racing, and basically everywhere Garrett's got its hand in professional motorsport, you'll see this range of turbochargers. Unfortunately for us mere mortals, we're never going to get access to them. Now, you just mentioned anti-lag as well, which kind of goes hand in hand with any form of rally. For those who don't really understand the technology, what anti-lag does, could you give us a real quick rundown on how that actually works, that strategy?
Yeah, probably aware when you go on the throttle, then there's a delay for the turbo to spool up and make the maximum boost. And then when you lift off the throttle, the turbo is going to spool down. So then when you go back on throttle, you have to wait again. The anti-lag strategy is to try to keep the turbo speed at a high constant value. So then whenever the driver is coming back on throttle, they have instant response. They have boost waiting for them. Maybe older school strategies would be to open the throttle so you get more airflow through the engine, which helps to spool the turbo. But then the engine's producing more power and can, want to drive in a straight line. So the ignition is retarded to make less power. And also retarding the ignition helps increase temperature, which provides more energy to spool the turbo to keep it up at your desired speed. Then with that strategy going through the engine, even with the ignition retarded, it will still produce a bit too much power. So usually some fuel cuts are used as well. So that's used to reduce the output of the engine. So if we didn't have the ignition retard in the fuel cut and we just opened the throttle, the engine would rev to maybe 5,000. But when we retard the ignition and then add the fuel cut, it will come back down to 2,500, 3,000 RPM, which won't disturb the driver as much. Then we can keep the turbo spooled up, but the throttle is closed, mostly closed. And you can have several bar of boost pressure waiting behind the throttle. So then as soon as they come in, they get instant response.
Okay, so that's the sort of strategy that I've personally had experience with myself, and it's effective, but there's essentially a limit on how aggressive you can go with that strategy, because opening the throttle further obviously makes naturally more engine power, so then requires more retard, more cut, etc., in order to stop the car from pushing. And at a point, the car will push. I use that term basically, as you were saying, just wants to drive away. So for a novice driver in particular, that gets quite off-putting when you get off the throttle coming into a corner and the car's still trying to drive forward. So that kind of becomes the limiting factor. These days, particularly in rallycross, we see fresh air anti-lag systems are really the norm now. Can you kind of give us a run through on how that system differs from an anti-lag system where we're opening the throttle body?
Yeah, so for the fresh air, we're connecting to an intercooler pipe before the throttle body. We're pulling air into a valve that then is allowing the air to go into the exhaust. So the earlier system was talking about flowing air through the engine, and now this valve is allowing the air to bypass the engine, so it doesn't produce that extra work. That the air going directly into the exhaust then is mixed with fuel and unburned fuel, and we retard the ignition so we have high temperature. So that's creating a burn inside the exhaust manifold, and that is keeping the turbo spooled. So it's almost like having a fifth cylinder in the exhaust manifold. that's much more manageable because then we can close the throttle further compared to the first system. And it's much tamer for the driver. So
as far as the driver is concerned, essentially the car would drive like a normal vehicle with no anti-lag system, but we've still got that advantage of the instantaneous response because the turbo's spooled, ready to go as soon as the throttle's cracked again.
Yes, and in the very slippery conditions like snow, ice, it could start raining and be muddy. Then if the anti-lag is too aggressive, they can really upset the car, upset the driver. So the bypass system is a big advantage there. I would say if you're working on that, I found having a thermocouple after the turbo is really important while you're trying to figure this out. If you inject the air too close to the turbo, or you have too aggressive of a system, you're going to create a burn, and that could be acting right on the turbine blade, and then you're burning the blade. So normally you would see a temperature drop across the turbo. So if you're just running without anti-lag, you might see 100, 150 C drop across the turbo. If you are using the fresh air or anti-lag, you should still see a drop across the turbo. But if the settings are incorrect, you might see the same temperature or a higher temperature. And then that's indicating that you have a burn occurring very near the turbine blade.
Sure.
And it's probably causing damage. So I know this is getting more accessible in the aftermarket, but there's probably not as much background about that. And
I think there's definitely a lack of information around setup and tuning. It's only recently we're starting to see some of the mainstream enthusiast manufacturers like TurboSmart release a product specifically for fresh air anti-lag. Obviously, the technology is not new, but it's starting to trickle down to the enthusiast level. So that is a really good tip, which kind of leads me to the next obvious question is, heat management with an anti-lag system is creating a huge amount of temperature in the exhaust system, the exhaust manifold, the turbocharger. Obviously, we've already talked about the advanced materials that those Garrett competition turbochargers use and their ability to run consistent 950C or above briefly. Does the upper limit of exhaust temperature, is that kind of your limiting factor for how aggressive you can be with your anti-lag tuning? Or does it still come down to just getting it set up for good driver feel and the driver feedback becomes, the key there?
Yeah, I think it's more about driver feel and feedback. If things are working well, we can be much lower than the limit of the EGT. We can be as low as 850C and still have good response. But everything is more quicker to react if we have higher EGT. So it's almost like that knife edge to your throat where you want it to be fairly high so you get really good response from the turbo, but you don't want to make a mistake and push it too high and burn the turbo because they're expensive and it can take them out of a race. So we're usually trying to keep things at a comfortable high level. It does affect the response of the turbo, but still have a margin, maybe 100-degree margin to not be right at the limit. One thing we talk about with the turbos, once you get them spooled up, there's sort of a minimum speed that you need to maintain for the anti-lag. And it's an analogy that is similar to like a jet boat. It takes a lot of energy to get it up on plane, but then once you have it moving, it's really easy to change directions. With the turbo, it depends on the size of the turbo and the size of the wheels. A big turbo probably will need to stay around 100,000 or maybe 105,000. If you go below that, regardless of how good your anti-lag system is, you're just asking too much from it to try to get it to come up or to stay it. If you're using very small turbos or a smaller turbine housing, it will naturally be more responsive. You might be able to get it down to 90,000 and still get good response. But there is a limit. Usually we're trying to stay north of 100,000 in order to keep good response.
Okay. One question I'm interested in here, is there such a thing as too much response with one of these engines? Particularly maybe for a non-professional driver, or maybe on a really slippery surface, can you end up with too much response, and here therefore do you end up pulling the anti-lag strategy down a few notches to dull it down a bit?
It's definitely possible. In addition to the changes that we've talked about, we can also change the throttle map, so the relationship between the pedal and the throttle. And that can have a huge effect as well. So if you have a lot of boost behind the throttle and it opens aggressively, it can really upset the car, especially if the driver is mid-corner, everything's kind of set up and they're trying to be very delicate. And they make what they feel is a micro change, but suddenly the rear end steps out because you've got a big increase in power. That can be really unsettling. So as part of the anti-lag strategy, we also work on different throttle maps, and the throttle map can go along with an anti-lag philosophy of how we want everything to work. People used to say you should turn the ALS off like in the snow or in the rain. Ideally, we don't want a system that will upset the driver that much. They should be able to drive it, not really notice that it's there. The response should be there, but it shouldn't be something that they're trying to manage or worry about.
On that note, do you give your drivers any in-car control over the aggressiveness of the anti-lag or adjustable throttle mapping, or do you just try and dial that in and give them one less thing to adjust or worry about?
In the rally car, there's 4 positions. So there's a road mode and then 3 stage positions. Some of them always go to the max, regardless of what it is. In the rallycross car, by regulation, we're only allowed on-off, basically. And the driver should not be adjusting it during the racing. Rallycross, they want no driver's aid, like traction control or torque control. So they want the driver just to have one switch to turn it on, and they can't be making any adjustments during the race.
Okay, fair enough. Let's move on and talk a little bit just briefly about the tuning. And again, you've mentioned you do everything in-house here, including the tuning. So what are you using here in terms of calibration, chassis dyno, engine dyno, all of the above?
Yes, we have an engine dyno, which is a hybrid water brake and electric motor setup. And then we have a Dyno Dynamics all-wheel drive dyno. Okay,
interested to sort of dive into that hybrid combo you just talked about with the electric motor and the water brake. Can you kind of clear up a little bit about what that is and how it works?
Yeah, we worked on that with a company called Power Test. So it's a Superflow water brake coupled to an electric motor. The electric motor can apply 200 foot-pounds of torque in either direction instantaneously. And the way the dyno is working is it sees the RPM error, what we're commanding versus what the engine's actually doing. The electric motor is the first to react, so it gives really tight control. But the dyno control system is always trying to go back to the water brake. So the electric motor grabs it first and then is releasing the torque to the water brake. The water brake has huge capacity. It can take 2,000 horsepower, but not as good control. So it's a blend of the two. When we're working on a hold at really high loads, and we're trying to hold a cell perfectly to make these adjustments, it was really causing too much trouble with just the water brake alone. It was moving, say, 50 RPM in either direction. We really didn't have tight control. And this hybrid combination has really improved the performance because we can focus on that and really dial in exactly where we want to be.
I must admit, my very first experience on an engine dyno was actually really disappointing. I'd come from a hub dyno background and initially hydraulic, and now I use the mainline eddy current hub dyno, which is really, really precise in its control. And what you're saying there about holding a cell, we could be within probably a few RPM of our target RPM almost irrespective of power, and that was what I was used to. And my first experience, which admittedly was a manual water brake dyno, engine dyno, and I sort of said to the dyno operator, I was tuning a Buick supercharged V6 Marathon jet boat motor, and I said I want to go to this cell here, and he spent about a minute just sort of driving around in circles around the cell before I quickly realized that wasn't going to work. I've since used water brake dynos with electronic control aftermarket fitted, and it's definitely effective, but you still get that hunting which you're talking about there. It won't hold precise, albeit the power and torque handling ability of the water brake is immense. So I understand the benefits there of adding that electric motor. And I think another bit that's really easy to overlook is with an engine dyno, typically because when we close the throttle, the engine just slows down. There's no real inertia there like we get out on the road. Chassis dynos are a little bit better in that regard, which I'll get to in a second, but that doesn't really exist on an engine dyno. So it's very hard to tune the light load, very light throttle areas. Impossible to do the overrun areas, and that, particularly when you're talking about the anti-lag strategy, that's where that operates. So I can only assume that's quite critical. Is that where that electric motor comes in as well, being able to essentially drive the dyno, drive the engine, and allow you to run in overrun conditions?
Yeah, we can run full lap simulations, so we can take data from whatever track we want, export it at 10 hertz. So we're exporting the throttle and the RPM. Then we're commanding the dyno to that throttle and RPM. And it's essentially recreating the car inertia, the car rolling down or braking. Although we're telling the dyno in one of these simulations go to, say, 2% throttle, essentially the throttle's closed. We're also saying the engine's going from 5,000 RPM to 4,000 RPM. And normally if we close the throttle, it's just going to idle down. So we can turn on ALS, we can run full simulations. And once we started doing that, we learned a lot. It allows us to tightly control what's going on and stop it when we want. So, the driver is out there doing laps and we don't know if we like it or not till we get the data back, where we could watch that live and say, okay, no, we didn't want to go that way. Let's try something else. And that's been a great tool for us to try different strategies, confirm what's working, what's not working, easily add extra sensors. It's very lively. It's exciting. We joke we need to put a firewall, like a car bulkhead up in a steering wheel, so we'll feel more confident. It seems like that's all you need to really push the engine. But it's quite a bit different than just running the engine in a normal mode, than having it in this full race anti-lag situation, turning laps. It's gets your heart going for sure.
Now, I can understand for validation and reliability testing that would be nothing would come close to that setup in terms of a chassis dyno. We just simply can't do that on the chassis dyno. For simplicity of testing and validation in the car, obviously a chassis dyno is incredibly quick and easy to use. How do you make the decision on when to use the engine dyno versus the chassis dyno, or is the engine dyno more a development tool versus sort of a quick test and tune?
We do all our development on the engine dyno, but then we use it for break-in and performance checks. So we have quite a procedure to go through. We have closed loop controllers. So we've got PID control for the water system, oil system, intercooler. So we can quickly identify if anything is out of spec, and a lot of redundant sensors, water flow, oil flow, everything we can to make sure that the engine that we're providing is healthy. And then if we're going through development strategies, we'll do that on the engine dyno. The chassis dyno is mainly used once the car is finished to check the entire build before we either go to a test or an event.
One question, because I don't often get to talk to someone who has both an engine dyno and a chassis dyno in the same facility, and this is the age-old debate that we'll never find a definitive answer to. But from your Superflow engine dyno to your Dyno Dynamics chassis dyno, what sort of a power differential do you see on the same engine once it's installed in the chassis?
It's about 15 to 18%.
Okay, perfect. That answers that for everyone across the entire internet from here on in. We don't want any more debate on that. 15 to 18%, job done. Right. If only it was that simple. But no, it is interesting always to sort of get a sense of that. And I mean, obviously, every dyno is different. Particularly, we also see differences in the power reported by a chassis dyno versus a hub dyno, because we simply don't have the power loss through the tyre contact patch as well to consider. So it's a moving target, I believe. Look, Dan, it's been great chatting, and there's been a mine of information that we've got out of you so far. No doubt we could probably continue for another hour, but I do want to respect your time, and I think we'll move towards wrapping this thing up, and we do finish off with the same 3 questions we ask all of our guests. The first of those is what's next for you, and maybe that's you or it's VSC in the future. Anything kind of on the radar that's new or exciting that you want to let us know about?
Yeah, I guess it's both for me and VSC. We have a big season coming up. We're currently in the ARA Rally Championship with 2 cars. We're going to do the Nitro Rallycross season. It's kicking off a little bit late this year. It's starting in October and carrying over into March. So we're going to do 6 rounds. We have released the new gymkhana car. The video hasn't released yet, but we've been working on that as well. So we've just got a ton of projects going on right now, which is...
Sounds like there's never a dull moment in the life of Dan, which is always makes it easier to get out of bed in the morning. Now, given your experience so far and your sort of training that you did to get you where you're at, I'm just interested, is there any advice you could give to a younger version of yourself, maybe to help avoid some of the pitfalls you've inevitably seen over your career and sort of fast track your progress?
One thing that helped me tremendously that I was mentioning early on when you were talking about, how did I get into this? I didn't really have a math, physics, science background. So when I got into school, I actually needed to start from zero, like basic algebra, and basically took every math class that they offered. After that, in 2013, I went back to school to get a master's degree in engine systems. And we studied some pretty intense areas like fluids and thermo. And where I saw so many people making mistakes was the basics. Like you learn a very complex topic and then you fail because you don't know how to do basic algebra or how to work with exponents. And I think it really is going to go into an engineering, physics-based field. It's described by math. This is how we're working with it to understand what's going on. Having the basics, I feel like it just keeps coming back to the real basics, helps tremendously.
So key there is stay in school, kids. Do your math
homework. In school, yeah.
I mean, I will sort of add the caveat there. You are operating at a very, very high level, and not all of our listeners, of course, are going to be striving to that level. So if you're sitting listening to this podcast and think that maybe you want to learn how to tune your own car, or maybe you want to work for a performance workshop, and you don't understand algebra, well, I mean, maybe that's not a deal breaker. There are levels to this, and you are at that upper echelon. And of course, at those upper echelons, yes, math is critical, physics is critical, and having a good handle on those fundamentals, as you say, is key. And I think what you mentioned there is so easy to overlook. You start with these basic principles and then layers of complexity get added on top. So where things fall apart is if you don't have the basics really dialed in, then when you start adding these more complex topics over and above, it's obviously going to be more difficult. So great advice there, Dan. Thank you. Last question for today. If people want to follow you and see what you're up to, maybe VSC, maybe yourself personally, any places they can go to?
Yeah, I would say if you haven't checked it out, there's a documentary series on the team called Launch Control. It's free on YouTube. It's on Amazon Prime. They're now going in the 10th season. and it closely follows all the activities of the team. It's really amazing production, and you get to see the behind the scenes of everything that's going on, good, bad, and yeah, we're really proud to be involved with that.
Amazing. Well, we'll drop a link to that in the show notes, and obviously Gymkhana coming out shortly, so we'll look forward to seeing the latest installment in that. Look, thanks heaps for your time today, Dan. Really appreciate it, and it really has been a deep dive on what goes into building cars at this level. So really appreciate you coming on this show today. Thank you.
It's been a pleasure talking to you, and I wanted to also say I've been a fan of your work for a while. And when there was the COVID lockdown, I think everybody was kind of stuck at home and trying to figure out what to do. I was home with my kids, like, okay, what are we doing? And I was really amazed that you guys opened up your gold webinars. So you put a ton of content on for free for people to access. And I watched a bunch of that, and I was just blown away that when people were hoarding toilet paper, you guys were freely giving away your goods. And I just thought that was an amazing thing to do. So I wanted to recognize that.
I appreciate the feedback, and I mean, it was a difficult time for everyone, and we know that there were a lot of people stuck at home during that time. We were among those, so I think there's only so much Netflix or Amazon Prime one person can watch, so education is key, and we're really all about just improving that level of education out there in the professional automotive industry. So yeah, thanks for the feedback. It means a lot.
Great, thank you. It's been a pleasure.
All right, that concludes our interview, and before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpaacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpaacademy.com/courses.